had 4 seasons, each predictable, each arriving on time. But now, the lines blur. Winters are warmer, storms grow stronger, and the skies shift without warning. Forecasting the weather was once simple, a calculation of patterns and cycles. But the world has changed, and with it our methods. Chaos lurks beneath the clouds, hidden in the equations that shape our future. So, how do we predict the unpredictable? Welcome to our weather forecasting. Weather is the ever-changing state of the atmosphere, a delicate balance of temperature, pressure, humidity, and wind. It shapes our world, bringing gentle breezes, torrential rains, or violent storms. But can we truly predict it? The answer is both yes and no. We understand the forces that drive weather: the sun's heat, the Earth's rotation, and the chaotic dance of air masses. We have satellites watching the skies, sensors measuring the smallest shifts, and powerful computers running simulations. Yet, despite all this, weather remains unpredictable beyond a certain point. Small changes today can lead to wildly different outcomes tomorrow. So, while we can forecast with confidence for the next few days, true certainty remains just beyond our grasp. Asterisk. Long before satellites and supercomputers, people looked to the skies for answers. Farmers relied on wind patterns, sailors watched the waves, and early meteorologists studied the shifting clouds. They observed how a red sunset often meant clear skies, while a sudden drop in temperature signaled an approaching storm. With only barometers, thermometers, and their instincts, they made predictions, sometimes right, sometimes disastrously wrong. Asterisk. As technology advanced, so did our ability to predict the weather. Scientists realized that weather follows physical laws, patterns that could be calculated. By collecting temperature, pressure, and wind data, they created early models to anticipate changes in the atmosphere. The telegraph allowed forecasters to share weather reports across vast distances, helping communities prepare for storms before they arrived. Today, forecasting is a high-stakes battle between nature and computation. Satellites orbit the Earth, scanning every storm and pressure system. Radar T-hours track rainfall in real time. Supercomputers run models that simulate millions of possible scenarios, turning data into predictions at an unprecedented speed. What once took days is now calculated in seconds, bringing the future to our fingertips. Imagine a world where every gust of wind, every drop of rain, every shift in temperature sets off a chain reaction. Unpredictable, uncontrollable. A world where small changes lead to monumental shifts. This is the essence of weather. But how do we make sense of such chaos? It begins with a simple truth. Weather behaves like a complex, chaotic system. Chaos. Unpredictable, untamed, yet not without rules. It governs our world in ways we barely notice, shaping the winds, the storms, the seasons. But what if we could glimpse the patterns hidden within? What if, buried in the randomness, there was a way to predict the future? Weather is chaos in motion, a delicate balance where the smallest change, a gust of wind, a rise in temperature, can ripple into something far greater. Scientists call this the butterfly effect, where a single flap of wings might set off a storm an ocean away. To predict the future, we had to first understand this chaos. We turned to the Lorenz system, a mathematical model that mimics the turbulence of the atmosphere. With it, we generated chaotic weather data, simulating the unpredictable dance of temperature, wind, and humidity. It was our first step in untangling the storm. In 1960, Edward Lorenz, a meteorologist and mathematician, uncovered a truth that shattered our understanding of prediction. He discovered that even the tiniest shift in initial conditions could lead to drastically different outcomes, an idea now known as the butterfly effect. At the core of this chaos lies the Lorenz system, a set of 3 simple yet powerful equations. dx/dt equals sigma, yx, dy/dt equals x rho, z, y dz/dt equals xy. Beta z. These equations describe how air moves unpredictably, forming turbulent spirals instead of neat, predictable paths. The values, sigma, rho, and beta, beta symbol, govern the intensity of this motion, determining whether weather remains stable or erupts into chaos. Imagine a single point in space. Our starting conditions, 0, 1, 1, 0, 5. At first, it moves predictably, tracing a smooth path. But soon, something strange happens. Tiny differences grow, twisting and turning through an invisible maze. The trajectory never repeats, never settles, yet it follows a pattern, an intricate dance of order within chaos. This is the Lorenz Attractor, a window into the unpredictability of weather. What seems random is, in fact, governed by equations shaping every loop and spiral. A slight change, just a whisper of difference, and the path diverges entirely. This is the essence of chaos, sensitive, beautiful, and impossible to fully control. But within this chaos, patterns emerge, and with patterns comes the possibility of prediction. Why does this chaotic system matter? Because weather itself is chaos. Small variations in temperature, wind, or humidity can lead to dramatically different outcomes. The Lorenz system shows us that even though weather is unpredictable in the long run, it still follows hidden rules. By understanding these rules, we can begin to forecast the future, not with certainty, but with probability. This is the foundation of modern weather prediction, transforming chaos into insight, randomness into patterns, and patterns into knowledge. To enhance the reliability of our chaotic weather data, we implemented moving average smoothing. This method works by averaging a set of past data points to smooth out short-term fluctuations and reveal the overall trend. By applying this technique to our temperature, wind speed, humidity, and rainfall data, we effectively reduced the noise from erratic changes. This helped us better capture the long-term patterns, offering more accurate and consistent predictions. The result was a clearer and more dependable forecast, essential for predicting future weather events. As we dive deeper into our forecast, we introduced a powerful technique called K-nearest neighbors. By analyzing past weather data, we identified patterns from the most recent conditions and compared them to similar past scenarios. The idea is simple. The most similar days to today, based on temperature, wind speed, and humidity, can guide us in predicting the future. With KNN, the model finds the closest neighbors in the dataset and uses their weather patterns to estimate what will happen next. It's like asking how similar days in the past turned out, then forecasting tomorrow's conditions based on those responses. By measuring proximity and similarity, we applied this method to predict key elements of the weather: temperature, wind, humidity, and even rain probability. The result? A more precise, data-driven approach to forecasting, providing a clearer picture of what lies ahead. Weather is a dynamic force, constantly shifting and evolving. From clear skies to thunderstorms, these changes unfold in complex patterns. By analyzing data and applying sophisticated models, we can understand these shifts. The more data we gather, the better we predict the unpredictable. As we enter the world of forecasting, let's dive into how we use mathematics to capture these chaotic systems. Here, you can see the code in action, where the Lorenz system visualizes chaotic weather patterns. The exponential moving average smooths out the noise, allowing us to better observe trends. Meanwhile, K-nearest neighbors works in the background, classifying data and predicting future behavior based on past patterns. This is where theory meets practice as we begin to forecast the unpredictable.
And so, from chaos to clarity, we've seen how these methods shape the way we predict the unpredictable forces of nature. With every equation and model, we move closer to understanding our world's ever-changing climate. Thanks for watching, and welcome to the future of weather forecasting. And as an answer for our question, we might say maybe. Who knows?